All right. In this example, we're looking at the Leslie model of populations. This is a common example of how to model populations for specific subgroups of females that are broken into distinct groups. And so in this example, we are given that the scooter bugs are divided into two age groups, one with less than a week old and one that are greater than or equal to a week old. And there's really not an equal to, it's just either you're less than a week or greater than a week. And so with that, then we see that the percentages that says that if you're less than a week, you have an 80% or 0.8 daughters per female are given on an average basis with a 40% survival rate for longer than a week. So this is the percentage of this population moving into the next category. Okay, likewise, we have that for in greater than 1 week, the average number of daughters being born per females in this group is at 0.5. And there is no moving on to the next category of ages since we only have this binary relationship or this binary group. So to set up the Leslie matrix for part 1 there, we're going to consider the Leslie matrix as given. So we have the two values here. So we're going to say this is 0.8 and 0.4. I almost have it set up exactly right there. And then this is 0.5. And there's no chance of going into the next generation for this one, since this is, there is just a bifurcation. So once you've graduated from being a week old, you're in the next group and that's it. And so this is our Leslie matrix for this particular case. Part 2, assume that we have 8 scooter bugs that are less than a week. That are, yeah, so this is, I should say n is less than 1. We have 8 of those, and then for n greater than 1, we have 11, I believe. Yeah, 11. Okay, so plugging these into and multiplying it out for part 2. Okay, so for the next generation we have 0.8, 0.4, 0.5, and 0. We're multiplying that by 8 and 11. Okay, and this gives us 11.9 and 3.2 after 1 week. Since this is kind of like a half-life problem in the sense that you have to wait for that unit of time to elapse for these numbers to be connected. This is the population. This is the population after 1 week. Okay. In other words, that's the life cycle of these. And so you'll notice that there are more younger females, less than a week, than there are females older than a week after that first population. Okay. And then it said 2 weeks and 3 weeks, so we'll need to take this as our new population, and we're going to multiply it again by our Leslie matrix. Okay, and that's going to give us then something like 11.12 and 4.76. Okay, so this is the second week. Okay, so first week, second week, and then I wanted us to find it for the third week. So let's take this population and multiply it one more time. So 0.8, 0.5, 0.40, and 11.42, 4.76. Okay, and that gives us then the result of 11.276 and 4.448. Okay, this is on our third week. Okay, so you'll notice that the population seems to be settling around 11. That's kind of interesting. Okay, all right, let's move on to problem 3. All right, so problem 3 said I wanted us to find the eigenvalues, so part 3. So we have 0.8 minus lambda, 0.5, 0.4, and minus lambda. It's 0 minus lambda, but I'm just going to write that as minus lambda. Okay, so if I set this equal to 0 and take the determinant, I get that lambda squared minus 0.8 lambda minus 0.2 is equal to 0, which implies that lambda is equal to 1 is the positive value, and we only consider the eigenvalues to be positive. So lambda equals 1 is our eigenvalue for this matrix. And let's see if we can plug that in. All right, so if we take lambda equals 1 and we plug it in to find the eigenvalue, that would be replacing each of these. So you get, this is negative 0.2, this is 0.5, this is 0.4 and 1, negative, plugging in lambda equals 1 here. Okay, we want to solve this system. Okay, so we set the augmented matrix, or you can think of it as just solving this outright directly. This gives us negative 0.2x1 plus 0.5x2 equals 0, and you'll see that 0.4x1 minus 0.5 minus 1, what am I doing? x2 equals 0. Okay, so that's a 1. So if we add all these together, however you think about it, this result is still negative 0.2x1 equals negative 0.5x2. So row reduction, or you can see that there's a redundancy here. In any case, we get x1 is equal to 2.5x2. Okay, which means that our eigenvector then would be of the form x1, x2 is equal to 2.5 to 1. So it's anything of this form. So that's the set of those values is the eigenvector, where we've chosen to let the linear combination of those. Okay, so this is the eigenvector for the lambda equals 1 is the eigenvalue. Okay, and then in part 4, that is part 4. Okay, and then in part 5 it says, what is the physical meaning of this context of the Leslie model? Okay, so how do we interpret this given this idea? Okay, and so we saw here when lambda equals 1, the interpretation to consider, if lambda is less than 1, what does that mean? It means that the population is going to go extinct. So when lambda is at less than 1, it means the population goes extinct. Okay, the question is do you see why? Okay, so that's what lambda is less than 1 implies. If lambda is greater than 1, kind of like the opposite of this, that means the population explodes. Okay, it will grow forever. In a normal model, of course, there are some physical limitations that will prevent that from going forever. There'll be some carrying capacity, but for the sake of this simple model, that's what it implies. And if lambda equals 1, like we have here, that means we have a stable population. One way to maybe think about this is the eccentricity of geometric figures, right? If you think about your Platonic solids, not your Platonic solids, your like your ellipses, your parabolas, and your hyperbolas, the eccentricity value has something very closely resembling the same idea. Okay, so this is the interpretation then, and one way to think about the steady state age, right? So we have the ratio from our eigenvector of 2.5 to 1 was what we had, which is exactly the same thing as 2.5 to 1 as a ratio, right? Well, that's the same thing as 2.5 to 3.5 which is times, if we multiply that by 100%, right, we get that this is equal to 71.43%, and 1 out of 3.5 times 100% is 28.57%, which is less than 1 week and greater than 1 week, which closely models our values for week 3. We look back at our results from week 3. Okay? All right, I hope that was helpful, and I'll see you in the next video.